So let's go to slide 46. So just look at starting. Starting of induction motor. So motor starting. Okay, we know we have different ways, different methods of starting motor, right? We have direct online starting, yeah. We have start delta. If you start a motor just direct, you know, what do you think will happen? It will draw a very high inrush current, yes. Okay, which is a big loss, you know. So we'll look at why do we need to use a star delta method. Okay, there are different methods of starting. I also have a soft starter. You can use a soft starter. You can use a VSD. You can use a liquid type. Okay, variable resistor. So a whole different methods of starting. Now, if you start an induction motor direct online, it draws a very high inrush current. Most of our motors are connected in delta. So instead of us to start direct, what we do first is we connect the motor on star, start it first. Look, if you have, let's say you have this like that, let's say 3 ohms, 3 ohms, 3 ohms. If you connect this in delta, the same 3 ohms you have in delta, 3 ohms, 3 ohms, what will happen? What will happen? The current will increase. Okay. If you have a data connected system like that, and in this format now, the current is going to increase. And we need to know the relationship between the current in delta and that in star. Right? So the current in star, let's just write this. First of all, we have that I star will be I delta over 3. So in other words, this star current, this current that will flow through here, okay, will be almost like 3 times of what will flow through here if it is star connected. So that's the first thing we need to know. So now, knowing that our motors are connected in delta, the essence of having this in delta is to have a high power, and to have a high power means to have a high torque. We have, because we know that P is 2 pi nt. So if you have high power, you get high torque. So that's why our motors are connected in delta. But the problem now is that when you connect in delta, on starting, it draws a very high inrush current. So the best thing will be to start it in star, and during operation, we reconnect, okay, that in delta. And we know that torque is proportional to voltages. Okay, torque also is proportional to voltage squared, the amount of voltage. If I even check this, if we check just a phase like that, phase value, all right, the phase here is already a line voltage. Okay, V line. And we know that this is a high torque. This one has high torque, because it has high power. Okay, when you connect in star, the power is a little bit lower. It draws lesser current, and then, so the inrush will be small. That's why we start with the star and delta. So, in other words, we can have that the torque on star, okay, over torque on delta, 1/3, just the same thing with the current. So in other words, 3, or the torque on star is 3 delta. So in other words, if you start like this, if you start with a star connected, the torque will be small. Immediately you connect to delta, now it increases torque by 3. Okay? So just need to know that. So the torque in delta will be 3 times of the torque when it is star connected. All right, I think that's a few things we should know, and then we can now use that. Let's look at this question in June 2017. June 2017. Okay, the first thing, let me just put what we have here. We have, remember that I said direct online which means now you are just starting it the way it is. Okay, it draws a very high inrush current. Okay, so now let's look at this question that says star delta starting is used on a 45 kilowatt 3-phase 525 1440 RPM motor with a power factor of 0.85 and efficiency of 92%. Now the motor draws 6 times its full load running current and produces 2.2 times its full load running torque when it is started direct online. Now, it says establish the current drawn and the starting torque when it is started by means of a star delta starter. Okay, let's write the values, all the things that are given to us first before we establish the parameters. So this is 2017, June. So it's a star delta starting is used. So star delta starting. So it's used, and the 45 kilowatt 3-phase 525 volts 140 RPM motor, power factor is 0.85, efficiency is 92%. Right, now the question says, it says the motor draws 6 times its full load current running 6 times its full load current, so 6 times I full load on starting. As we said, if you start a motor that's online, it draws a very high inrush current, 6 times its full load running current, and produces 2.2 times its full load running torque. 2.2 times full load torque. This is on direct online starting, where it is started direct online. Okay. So this is I, direct online. This is T, direct online. Okay. Now establish the current drawn and starting torque when it is started by means of the star delta starter. Now number 2 is to determine the full load line and phase current when running in delta. Okay, so we have starting the motor in star, as we said. If we start the motor in star, let me see this again. Remember what we said before, that if you start the motor in star, I star, 3 times of it will give you the same thing as I delta. Even the same thing with that of torque. Torque star is torque delta. Okay. So it says starting. So the question there says to determine the full load line. Sorry. Say establish the current drawn and the starting torque when it is started by means of star delta. Yeah, this is 6I full load on direct on line, and this is a 2.2I full load. Right now, if we are using now star delta, starting, in other words, start with a star first, and then you switch to delta. So the we must determine the current drawn, establish the current drawn, and the total torque when it is now sorted as a star delta. So we have this. I can write here that I delta will now be 230 volts, 50 hertz, capacitor start motor has the following constants for the main and auxiliary winding. So this is but if it stops running, you can't start it without the capacitor. So that is how a centrifugal switch and works. All right. So now, so if you have this, let's see what they said. Determine the value of the static capacitor that will place the main and auxiliary winding currents in quadratio. Like if you want to put this, a capacitor, how much capacitance are you going to put here so that the angle between this and that, okay, is 90. You want the angle between the auxiliary and the main winding to be 90 degrees. So I need to put a capacitor there. So what you do is you saw right, this is Z. Z of the main is given to you as 4.5 plus J 3.5. And then the Z of the auxiliary is 9.5 plus J 3.5, right? 9.5 plus J 3.5. Okay, this is 3.7, the first one. 3.7. Okay, so this is the main winding, this is auxiliary winding. Okay. Now, there's now said, how much of capacitance can you add here to make the phase angle difference between this and this to be 90? Okay. Quadratio is 90 degrees, right? When we hear about quadratio, we'll talk about 90 degrees. So remember that this one, if you look at this, if you use your calculator, just to punch this, let's put the impedance, let's put this in impedance, 4 point, should give you 4 Z main. Is it 3.5 or 3.7? What is that?
3.5.
But they put 3 point
Or they put 3.7 on top.
on top. Okay. So which one can we take? It's just a mistake. Which one can we take?
I think the 3.7 is like they use 3.7 in the calculation.
Okay. So let's get 4.5 plus J 3.7. Just put it in polar form. 5.83.
At an angle of 59.4.
All right. So now this one, right, will be another value. Will be a certain value with an angle, but let me just put the angle first before I come and I explain. Can you put this one in polar form also?
It's 10.12. The angle of
Now, when you check, remember there's no capacitor here. When you check these two angles, they are now phase shifted by 90, right? So what we want to do is we want to put a capacitor. In other words, this is 9.5 plus J 3.5. We want to put a capacitor. Remember, I just put minus because it's capacitance, okay? Yes. I want to put a capacitor so that the angle, so if I put a capacitor, I'm going to have something else now. I'm going to have a different value from this. Something with a certain angle, but the difference between this angle and that angle must be 90 degrees, right? So what I'm going to do first is, for us to have okay, but it's live now. I'll soon answer once I'm done. Okay, now, so now, where are we? Okay, so now, let's explain here. I hope we know what this thing means, like just this one, this ZM. ZM means like that. ZM, this angle is 39.4, right? Agreed? And this is the active side, 4.5. This is the reactive side, 3.7. Okay. So now what I want to do is this. If this is our reference point, now I want this one because this one now is capacitive. Capacitive. I want this, the whole of this angle, right, to be about 90. If I'm going to get this to be Z auxiliary. So remember that I want to make this reactive, capacitive. That's why I'm going to have a lagging side, all right? Okay. This is leading for inductive, for capacitive.
Yes.
Okay. Now, what do I do if I want this angle to be 90? I want to know the angle of this auxiliary. What will it be for the angle between this and this to be 90?
50,
so it will be, I want the angle of the auxiliary to be 90 minus that, right? 39.4. You say it's 50.6. Yes. So that is what I want. I want this angle. And how do we get the angle? If you check here, how do we get this angle? We said you can use tangent, cosine, or whatever. So for instance, cos theta is opposite. Tan theta is opposite over adjacent, right?
Yes.
For that. The same I can do that. If I want this to be like that, where this one will remain the same, it's not changing. Look at this. The active side is not changing. Yeah. The one that is changing is here. So this, and I want this angle to be 50.6. So if I want to know that total capacitance, okay, capacitive reactance, this is the capacitive reactance, which is the whole of this. Okay, the imaginary side, isn't it? All right, so I can just say also opposite of adjacent tan 50.6 equals xt over 9.5. So that xt is 9.5 tan 50.6. But this x is capacitive. Okay. It's capacitive, all right? So what is it? 9.5 times that, we'll get 9.5 by tan that. What do you have? So we have tan 50.6. So have 11.56, right? Or 57. So let's say 11.57. This is capacitive. Because the total thing, we want for this to have a phase angle of 90 means One was inductive, one was capacitive. Okay, so that means the whole of this must be equal to that, right? So that means that 3 point from here, okay, 3.5 minus x of the capacitor we are bringing in must give you minus 11.57. Okay, it must give you that. All right, so that when you take this one to the other side, you bring these other ones here, 3.5 plus 11.57 will now give you the capacitor, the capacitive reactance that you need to bring into this to create that quadrature. And once you get that, that to be about 15.06. 15.07. Okay. This is in ohms, right? That is the amount of capacitive reactance that you need. Okay, 15.07. Before you can now convert it to this thing by saying XC is 1/2 pi FC. Okay, just to get the capacitance. So you make capacity subject. We say this is 15.07. So you just make C the subject. Right? That's our C will now be 1/2 pi F by 15.07. Okay. So when you do that, you can get 211 microfarad. Did you get that? Okay, I just want us to have that in case if anything happens. Okay. Did you hear that? He said audio is very low, right? It's increased. Okay, so that's all about that. No, not yet. What time is it?
Yeah, finish with this.
Yeah, we're done with that. What time is it now?
Time to pause.
Yeah, I forgot. I thought you've forgotten. Yep. All right, so now let's did you make a printout of the synchronous motor?
Yes.
Oh, you have it? Okay, so let's start with okay, we'll look at synchronous motor. Synchronous machine. All right, so now remember this synchronous motor or machine is almost like It's almost like a DC machine. You know what DC machine, what we did? We had a field winding, we had armature winding, right? For induction motor, we had the stator winding. The armature was what was also called armature, but which is a rotor. We just had bars, solid bar, copper bars, okay, that we call the squirrel cage. And then there was no supply to it, okay. But if you remember our DC motor, we had like that, for instance, like that. We had a supply to this, and we had a supply to that, if you remember, right? So that this one will create its own flux, that one will create its own flux. We are going to use the same principle of a DC machine for a synchronous machine. All right, so because now for induction motor, we say it's like it's a rotating a transformer with rotating secondary. So the secondary terminal, we only shorted it. But what we are going to do is we don't have to short it. It must have its own source also. So that we create its own field, and this one will create its own field, and they can lock. So if this one is rotating, if the stator field is rotating at a synchronous speed, it can lock with the field of this one, so that the rotor of that generator will also rotate at the same speed with the rotating magnetic field. All right. So now now we have a constant speed fixed. Okay, in this case, the speed is going to be constant. It's not going to change. And for us to do that, we are going to provide an excitation. We are going to create our own magnetic flux. Remember what we did in an electric motor? A DC machine. We have our windings, but this one here is that internally there was no winding. So it was waiting for power, this one to be powered, and then induce EMF into this, and this one to create its own flux, you know. But in this synchronous motor, instead of doing that, we are going to also excite this. So this guy must have his own flux from its own source, and this one must have its own flux from its own source. So as this is having rotating magnetic field, then this one can lock with it, okay, and rotate at the same speed of 120 F over P. That's the difference between induction motor and synchronous motor. Synchronous motor runs at constant speed regardless of how you load it, except if the load is now more than the rated load, the rated torque, then it can pull out, it can stop. All right. So the first thing is that the speed of the motor can rotate at a speed of the rotating magnetic field. So if you check what I sketched there, on the armature side, you have your windings with the three-phase current in. Even on the rotor side, it has also its own winding, okay, with a source to create its own field. All right. Remember, we are trying to see how we can cover a semester work in 20 minutes. But is it possible? Yeah, it's possible. We've done it before, so we can still do it again. All right. It's a lot of work, I know. Synchronous machine alone is a serious thing. Okay, but it's fine. Let's see how far we just go. Few things. Okay, we have different kinds of rotor. We have our salient pole rotor. The salient pole rotor produces a lot of harmonics. Okay, so most times it produces third harmonics. All right. Let's look at this. Now, we are going to represent a synchronous machine the same as that of a DC machine. Remember the DC we supply, because now we have two supplies. Look, this one is coming on the stator, and this one is also the rotor. So you have two windings. Okay, so the same thing we had in DC motor. And in DC motor, as we have also here, so we're going to have a supply, we're going to have the windings of your armature like that, and then you still have that. So you're going to have your V, the voltage input. Now on the rotor side here, there's also a supply, right? So which you are going to have that, which we say you are going to excite the machine. So now this is just to represent it, make it look simpler. So it's a voltage in, and then this is a back EMF. Remember what we said. When a voltage gets in, and this is rotating, now as this is rotating, if we cut across the winding, an EMF will still induce. And that induced EMF will oppose what is producing it. So you are still going to have a back EMF. So now, what you have here is your synchronous impedance, ZS. We call this ZS. Remember in the DC motor, we have only resistance RF. Okay. Now remember we're not dealing with AC. So with AC, we don't deal not just R, but there must be an impedance. Okay, so we still write the same equation by saying this voltage that you have will take care of current flowing I by Z plus E back, the back EMF. So we still have the same, just like a what is it called, like a DC machine or DC motor. So we have that terminal voltage equals E by plus IZ. Okay. Let me see what again that we need to know. I think I have just get a few things here. All right, so now, as I said, just because there are too many things, so we just need to look at one or two few things there and solve the problem. Okay, let's look at the equation. Let's just have a look at this equation. You know what I say? I call this synchronous impedance, right? Now look at the question says a star-connected three-phase synchronous motor takes 93 amps at 500 volts. Remember, it's a star-connected. Star-connected. And it takes 500 volts. The unity power factor has an armature resistance and reactance per phase of 0.03 plus 0.3 ohms, respectively. So we are given this now. 0.03 plus J0.3. That is your ZS given to you. Okay? Agreed? Now, sorry. Now, and assume efficiency of 94. Efficiency 94. Now you are asked to calculate the rest. Remember what is a three-phase system. It's not a DC source. But just make sure that we are going to represent this, we'll know that from the onset that this is a three-phase, which is being represented as a single phase here. All right, they want us to calculate the full load. First, the full load current at a power factor of 0.8 leading. Look, the power, it's a star connected. I is 93 amps. And 3 amps at 500 volts. And then ZS, Z impedance ZS plus J 0.3. And then also efficiency 0.94. All right. So it's a three-phase. How do we, what is the power? Power is √3 IV, right? Cos theta. Agreed? Right. So now, but now the power is going to, the current is going to draw the power in. We must also consider even the efficiency to get the exact power in, because it says it takes full load at 33 amps at this, the unity power factor has that resistance, and then they want to calculate the full load at a 0.8 power factor. In this kind of question, there's many ways of solving it. The first one, do you know that power factor is inversely proportional to the current? If power factor is low, what happens to the current? It goes up. Yeah. Power factor is inversely proportional to that. Or I is inversely proportional to power factor. So you can even use this one to solve the problem. I mean, because they said we are giving this, they said it's 93 amps at this, and then what will be the full load current at 0.8. And this is at what unity power factor. So what do? You can use this. Okay, you can just write that I1 by I2, power factor 2, power factor 1. Okay. So if they say you should get the I2, the full load current at 0.8 power factor, then have that I2 equals to I1 power factor 1 or power factor 2. And I1 is 93. That's power factor 1 is 1, and power factor 2 is 0.8. So you use this to get how much current it will draw. It will draw a very high current, something higher, when the power factor is low. Okay, so 93 point that, what do you have? 93 divided by that, you get about 116. 93 divided by 0.8, 116.25. Okay, you get that as 116.25. Okay. If you want to use this other way, you can calculate the power, the active power, which is not going to change. The reactive power can change. You use it as an active power √3 by 93 by voltage. Cos theta is 1. You leave it as constant P. Now you say, okay, S is IV, and the P, new P is IV cos theta, okay, √3. Okay. All right, so, but you can use this like that and solve and get 116. Now let's look at the next one, is total mechanical power developed in kilowatts. Mechanical power developed. This is a motor. It's a motor. So with the motor, you're going to have power out. And they want us to calculate the total mechanical power developed. We have the current in as 93 point that, but we are given the efficiency. The efficiency there is assuming efficiency of 94. Can we get power developed?
Efficiency is power out and power in.
Efficiency is P out by P in. And P in is √3 IV cos theta. Okay. Agreed? So we have root 3 here. We have 93. We have, okay, at, they didn't tell us whether it's at 0. Okay, let's solve at 0.8, right? Yeah. So if I'm to solve at 0.8, I'm not going to use 93 in this case. Or if I want to check, let's check what will be the power developed at 93, because at that 93, this is 500, but this is 1, just at 93. Okay. So now you just multiply this by that. To get power developed, P out will now be whatever you have here by 93 by 500 by that efficiency of 0.94. This is a power that will be developed when it's operating at a power factor of 1. Okay. Power developed. Okay, but if you want to get power developed when operating at the power factor of 0.8, we're going to substitute 0.8 there, where we have 1. We'll multiply that by 0.8 again. Let's see how much that one can give us first. That is root 3 times 93 times 500 times 0.94. That's 75.7. Okay, 75.7 kilowatt. Okay, the power developed. Okay, which is the answer there. Now, okay, this one is just normal solutions. Now, the essence of doing this equation is for us to apply this, right? Which is the last equation there. The electromotive force generated by the motor. This one, the back EMF. For us to calculate the electromotive force generated by that motor. Okay, so now if you want to calculate that, so we go back to our equation. If they said you must calculate that, you have EB, okay, to be V minus IZ. V minus IZ, right? V minus IZ. So did we get our I? We have our I here, right? At that power factor. Now, if you complete this, remember that this is with arc cos of 0. I mean, yeah. Like if you just want to put that power factor, okay, you put the angle, isn't it? This is this over there by power factor. Now, this is 116.25, but the power factor, okay, that gave us that 116.25 is arc cos of 0.8, which is arc cos of 0.8 to get the angle itself. All right, so it means here I is let's say arc cos of 0.8. We give it 36.7 or something like that. Now let's calculate this. Now, what voltage am I going to put here first? What voltage? Just want to check if we know what we are doing. What voltage can I put here? Because I want to now solve EB. What voltage can I put there? 500. Is it true? What voltage can I put there? What is V? Okay, remember this is a three-phase system. And like this, what is this? It's a single phase, right? So what voltage can I put there? 500 over root 3.
Yeah.
Okay. For you to, you need to resolve. Huh?
That's 303.
Yeah, so have 500 over root 3. Is it 303, right?
Yeah, 303.
Okay, then minus, you now put the current to have 116.25 with an angle of 36.7 into 0.03 plus J 0.3. Okay, like that. 116.25 okay, so when you do that, you get something, you get a value. As I said, the essence of doing this is just for us to apply that. But as I said, this is just a single phase representation. But knowing that since it's a three phase, and not only three phase, it's a star connected three phase. So this voltage between the two lines is 500 volts, but now we've resolved to this, we've resolved that to a single phase only, one winding. So one winding. So which voltage there with 500 over root 3. Okay, that's how we got that one. And minus the current flowing, okay, multiplied by the ZS. Okay, from there you get your electromotive force generated. Okay. Okay, another question again that was asked some time ago, 2006. Well, this is 2013. And it's about 10 good marks, isn't it? So I'm sure you can solve it if you have a question like that. Just make sure we touch all the things we are supposed to do. Now, can I clean? Okay. Okay, so let's just look at that question there. Can I clean? All right, so now look at that question. It says specifications are to be written for a three-phase 50 Hz synchronous motor for a rolling mill drive in a steel plant. Points on the motor duty cycle estimated on the basis of the proposed rolling schedule and previous experience with mills of this type are given in the table. So you have that table there. Now the complete curve can be obtained by joining these points with straight lines. The question is to specify the continuous power rating of the motor. You want to buy a motor that can take care of that duty cycle. You're not going to buy a thousand kilowatt motor. We know that we know the maximum load there is about 1,050. If you buy that, hey, you are just going to spend money for nothing, because the motor is loaded for short time, all right, between 36, from 36 to 39, about 3 minutes, or 3 seconds, in fact. So it will just be a very big waste if you buy such motor. And you might not buy a 120 kilowatt motor. If you do that, it means that in some stages, your motor will be overloaded. So you need to get something average. And to get the average, we are going to plot the graph of power versus time. If we plot the graph of power versus time, so we know that our energy is power times time. In other words, if I plot that graph, the area of the graph will give you the energy. And if I take that area, divide by the average time, okay? If I take that area, which is power times time, divide by average time, right? Time, then I'll get back to my power. So I'll get an average power. So what we are going to do is we are going to plot the graph just as we have it there. The first time the motor is loaded at 120. Just first time, initial loading, 120 kilowatt. And after 120, 820. Now, I need to check, because I need to put up my scale very well here. So I'm going to check the highest. Highest is 1050. So I just need to see how I'll move this to get about 1050. So even if you don't put a scale, you can put 1050 there. You can put, the next one is 820. 820. You can put, after 820, have 300, right? 300. And that's all. So you have 120, 820, 1050, 300. Okay, that's all. Now let's now put your time in. Our time is 0 to 80 seconds. So that means I have 10, 20, 30, 40, 50, 60, 70, 80. Okay. So I just need to plot this, that I'll be able to get my average power, my average energy. I can divide by total time to get my power. So now the first one is 0 with a 120, so I mark here 0 with a 120. After 5 minutes, you have 5 with 820. That's a 5 minutes. We'll have that. This goes up there. It's 5 minutes. After 5 minutes, so it picks up load up to 820. Then after 36 minutes, 36, you have 1050. That's 36 somewhere. Hmm? 0. So now 36 is 36 with that. So this can join there. And then 39 with 300. 39 with 300. So this comes down. That is 39. And then after that, 55, 120, 55, 120. Then after that, 80, 120. 80, 120. So you have this, and then you have that. So we'll take this energy, then you have this. I have that, and have this. So I'm just going to add these areas, the area A, B, C, D, E. Okay, if we add them together, we'll get the total energy. Okay, and then we can now from there calculate average power. Okay, how do we get the energy? I said the energy, which is power times time. Power times time is just the area of this, and this is a trapezium, where you have these two adjacent sides, this one and that one as two adjacent sides, and this as the height. So area of a trapezium is the sum of the two adjacent sides times is half of that times height. Half of the sum of the two adjacent sides times height. Okay. So now, if I want to get energy for A, so I have to add this from here to here, 120 plus from here to here, 820 by 2 times height, 5. So this will give me the energy here. We do the same thing for energy at B. Energy at B will give you also, this is sum of the adjacent sides, which is 820 plus 1050 divided by 2 times from here to here, 36 minus 5. Now, later you do this, energy C, sum of the adjacent sides, 1050 plus 300 divided by 2 times from here to here, 39 minus 36. Now energy D, sum of the two adjacent sides, which is 300 plus 120, 2 times from here to here, which is 55 minus 39. Okay, that's ED. And then you also do EE. It's just length times width, which is 120 times from here to here, times 80 minus 55. So once you get these energies, now energy total, so you just add them together. Okay. All right, so that is what we have there. You have total energy. You just add the total energy together so that E total will be EA plus EB plus EC plus ED plus EE. So which, if you add them together, you get 39720. 39720. So to get a power, average power P is E total over time, which is 39720 divided by 80 seconds. When you do that, you get 496.5 kilowatts. So this is about the size of the motor that you can buy for this application. Okay, so we'll continue next week on this, and also we start with compressors by next week. Okay.